Last time I introduced the definition of Schouten tensor and Weil tensor. Today I want to show how these two tensors change if we make a conformal change of the metric. So we say that two metrics G and G tilde are conformal if G tilde is equal to the product of a smooth positive function f times G. I'm going to write down some formulas, and these formulas looks much simpler if I assume that G tilde is equal to e power 2f times G, where f is a smooth function on M. The first result I want to present without proof is this proposition, which is about the conformal transformation of the Levi-Civita connection and it says that if nabla and nabla tilde are the Levi-Civita connections of the Riemannian manifolds M, G and M, G tilde with G tilde equal to e power 2f times G, exactly as this formula. Then this formula holds true and the Christoffel symbols of these two connections are related by this formula. The consequence of this formula is a theorem conformal transformation of the curvature that I will not present entirely. I will focus only on the formula for the Schouten tensor and the Weil tensor. So suppose that M is a Riemannian manifold of dimension larger or equal to 3, then if P tilde W tilde are the Schouten tensor and the Weil tensor of G tilde equal E2F times G, then we have that P tilde is P minus action of F plus dF tensor dF minus 1 of dF square times G, and surprisingly W tilde is just e power 2F times W. This formula has an important consequence, which is formulated under the form of a corollary that I can present after giving you a definition. A Riemannian manifold is locally conformally flat if every point has a neighborhood that is conformally equivalent to an open subset of the Euclidean space. Now I can present the corollary. Suppose that this is a Riemannian manifold of dimension n larger or equal to 3, then if G is a conformally locally conformally flat, then its Weil tensor vanishes identically. The proof is very short. So suppose that the manifold M with the metric G is locally conformally flat, then for every P in M there exists a neighborhood U and an embedding phi into Rn such that the pullback of the Euclidean metric is conformal to G. That is equals G tilde equal e power 2f times G So this implies that W tilde is identically 0, and then using the fact that W tilde is related to W by this formula, this says that also W is 0. So this corollary says that if the manifold is a locally conformally flat, then the Weil tensor is a zero. We could ask ourselves whether or not the converse is true. The answer is yes, if the dimension is at least 4. This theorem has two statements. The first one is about the Weil tensor, and it says that if Mg is a Riemannian manifold of dimension n greater or equal to 4, then it is locally conformally flat if and only if W identically 0. What happens if n it is equal to 3? If n is equal to 3, W is always 0, so we have to introduce another tensor known as Cotton tensor. C is defined as minus the exterior covariant derivative of the Schouten tensor. I want to recall the definition of the exterior covariant derivative. After that, I will write down the statement number 2 of this theorem. If you have tensor T, smooth two tensor fields, then the exterior covariant derivative of T is a 3 tensor defined this way. And in terms of components, you can write this formula. So if you use this formula, you can get that Cijk, this is Pij semicolon k minus Pik semicolon j. If Mg is a Riemannian manifold of dimension 3, then it is locally conformally flat if and only if C is identical to 0. And now we change completely the topic, and let's talk about Riemannian submanifolds. So in the sequel, I will suppose that M tilde G tilde is a Riemannian manifold of dimension M, and we will call M tilde the ambient manifold. I will suppose that Mg is an embedded Riemannian manifold. Sorry, let's write embedded Riemannian submanifold of M tilde, and our goal is to write down the relation between the connection, the Levi-Civita connections of M and M tilde. In order to do this, I want to introduce some notation. So pi tangential is a projection from Tm tilde restricted to M onto Tm, and pi orthogonal is the projection from Tm tilde restricted to M onto the normal bundle, I want to recall what is the normal bundle. This is the disjoint union of the normal space to the manifold M, which is defined as the orthogonal of TPM. It is possible to prove that TPM tilde, this splits as follows. These projection here are less complicated than you think. In fact, if E1, E2, EM is an adapted orthonormal frame for M in M tilde, then this projection here, sorry, before erasing, I did not write on the blackboard that this is called normal projection. I'm sorry. So the tangential projection this is a projection onto span E1 En, where n is the dimension of M, and the normal projection is a projection onto the span of the remaining vector fields. Unfortunately, I have to erase. So other notation that I will use. So if X is a section of the restriction of the tangent space to M tilde to M, then X tangential given by pi tangential X is the tangential part of X, and X orthogonal is the orthogonal part of X. So if x and y are elements of key of M, we can consider their extensions to vector fields on an open subset of M tilde, and we call these extensions x and y. Then it makes sense to compute this covariant derivative, and it is clear that if we look at points of M, this decomposes as follows. Nabla tilde of y in the direction of x tangential plus nabla tilde x y orthogonal. Now we try to give a geometric interpretation of these two terms. We start with the second one, and we give this definition. We define the second fundamental form of M as a map denoted by this symbol, which is red saying 2, from K of M times K of M into gamma NM, writing 2 of xy equal to nabla tilde xy orthogonal, where x and y are, of course, the extension I introduced here. Since this is the image of the map pi orthogonal, which is smooth, this is clearly a smooth section of NM. So this explains why 2 takes value in gamma NM, that is a set of sections of NM. The first result I present without proof because it's very easy, is the following. If x and y are in K of M, then you can prove the following statements. 2 of x, y is independent of the extensions of x and y. B 2 of xy is bilinear over C infinity m in both x and y. C 2 of xy is symmetric D 2xy at P depends only on xp, yp. That is the values of these two vector fields at the point P. The reason why the second fundamental form is important is provided by this theorem known as Gauss formula. So suppose that Mg is a Riemannian submanifold embedded in M tilde So if x, y are extended to smooth vector fields, on a neighborhood of M in M tilde, then we have this important formula along M. I want to explain the idea of the proof. So we already know that this splits as follows. And this is equal to this. So what we have to do here is just to prove that this is equal to nabla xy. The idea for proving that this term is equal to this is the following. We define nabla orthogonal, nabla tangential, writing this way. And what we have to do is to show it is the Levi-Civita connection on M, then the uniqueness of such a connection implies that nabla tangential coincide with nabla, because nabla is the Levi-Civita connection of M. This formula has a corollary if we consider a different setting. Precisely, we work with curves and vector fields along curves. So suppose that gamma is a smooth curve and X is a smooth vector field along gamma that is everywhere tangent to M. Of course, I am assuming that M is an embedded Riemannian submanifold of M tilde. Then, using this formula, we can prove that the covariant derivative along gamma with respect to the connection of M tilde of X is the covariant derivative along gamma with respect to the connection of M of X plus 2 of gamma prime X. Okay, let's see the proof. So we fix T0 in I, the interval on which gamma is defined. So find an adapted orthonormal frame E1, E2, EM in a neighborhood of gamma. Sorry, I don't need to write of. around gamma t0. If X is a smooth vector field along gamma, then I can write X as follows: xi t ei restricted to gamma t. Then the covariant derivative along gamma of X with respect to the connection of M tilde can be written down using the product rule. So I have X dot I ei plus xi nabla tilde gamma prime ei. Now, for this term, I will use this formula. And I get X xi nabla gamma prime ei plus xi 2 gamma prime ei, and by linearity of 2 I get that this becomes xi ei plus xi nabla gamma prime ei plus 2 of gamma prime x, and the first term is exactly dtx. And this is the end of the proof. Now let's observe that the second fundamental form is being defined in terms of covariant derivatives of vector field tangent to M, but it can be used also to evaluate extrinsic covariant derivatives of normal vector fields. So let's give this definition. Suppose that N is a smooth section of the normal bundle. Then we define the map 2N writing 2n of xy equal to the inner product of n and 2xy. It's not finished. We define Wn from T of M into itself as the self-adjoint operator associated with 2n that is the inner product of Wnx y is equal to 2n x y, that is the inner product of n and 2xy. Wn is what we call Weingarten map in the direction of n. It is clear that this is a smooth bundle homomorphism from Tm into itself, because Wn is linear over C infinity m, and this is consequence of the fact that the second fundamental form is bilinear over C infinity m. The first result about the Weingarten map is this proposition, which is about the Weingarten equation. So if Mg is an embedded Riemannian submanifold of the Riemannian manifold M tilde G tilde, we have that for every x in K of M and in gamma and M, then the tangential part of nabla tilde x n is minus w n x when n is extended to an open subset of M tilde How to prove this result? Suppose that y is in T of m, and we consider its extension to an open subset of m tilde, then it makes sense to consider this product this is 0 along m. Consequently, if I take a vector field which is tangent to m, I have that this is 0. But this can be written as nabla tilde x n y plus n nabla tilde x y. We manipulate the second term using the Gauss formula, and we get n nabla x y plus n 2x y. It is clear that this is 0 because this is a tangent and this is normal. So we get nabla tilde x n y plus n 2x y, but this is wn x y by definition, and since y is arbitrary and tangent to m, this says that the tangential component of nabla tilde x n plus wn x, sorry, orthogonal, so the tangential part of this vector, this is 0, but clearly this is equal to nabla tilde x n tangential plus wn x, because wn x is tangent to m, and this says that wn x is a negative nabla tilde xn tangential, and we have finished it. The next goal is to describe the difference between the curvature tensors of M and M tilde, there is an explicit formula discovered by Gauss, known as Gauss equation, which says the following: for every W, X, Y, Z in T of M, then Rm tilde of W, X, Y, Z is equal to Rm of W, X, Y, Z minus the inner product of 2W, Z, 2X, Y plus 2 of W, Y multiplied by 2X, Z. Let's see at least the idea of the proof. First of all, we have to extend W, X, Y, Z to an open set of M tilde. So the left hand side now makes sense. Then this by definition is nabla tilde W, nabla tilde X of Y minus nabla tilde X, nabla tilde W of Y minus nabla tilde of the lead bracket of W and X of Y, and everything is multiplied by Z. Then you use the expansion for these two terms. And we have to use the Weingarten equation. So as a consequence, we get nabla tilde w nabla x y z minus I would like to say that when you use this formula, you have to replace once n by 2xy and n second time by 2wy, and if you will do this, you will get this term from nabla tilde w nabla xy then from nabla tilde w2xy using the Weingarten equation, you will get minus 2xy 2wz. Then similarly you will get minus nabla tilde x nabla w y comma z plus 2wy 2xz. I forgot this, and minus nabla tilde, sorry, inner product wx y z. You have to continue decomposing nabla tilde into tangential and normal components. And if you do this, you will see that you have to multiply the normal component of nabla tilde with z, nabla tilde of something with z, which is tangent. So you get 0, and this means that only the inner product involving the tangential part survives, but tangential part is the one involving the Levi-Civita connection of M, that is nabla. So this means that you have only terms like this. So from this you get this only. From this term you will get and from this you will get And then I just copy these two summands. And we'll finish it because these terms here are Rm W X Y Z. Let me check how much time I have. Okay. So we've seen that when we define the Weingarten map, we have considered the tangential part of this vector field. What happens if instead we take the normal part? We can define a normal connection as a map defined on Q of m times gamma and m with values in gamma and m as follows. Where n is extended to a smooth vector field on a neighborhood of m in m tilde. And you can prove the following result. Nabla orthogonal, the normal connection we just defined is a well-defined connection in the normal bundle, which is compatible with g tilde, that is for any n1 and 2 in gamma and m, for every x in T of m, we have that this is true. Okay, I think it is a good point where to stop. Thank you for your attention.